Let's work through an old exam question from the Northwest Province, September 2017. And this question uses equilibrium and stoichiometry. So here is the question. We're going to focus on 6.2, the calculation question. So you should read this question, try it yourself, pause the movie until you've done that. So this is about the Haber process, nitrogen reacting with hydrogen to produce ammonia. And we're told that we start with X moles of nitrogen in the beginning and 8 moles of hydrogen. We add them to one another in a 5 decimeter cubed sealed container. So that's the volume. Now, it doesn't tell us anything more, but it implies that there's 0 moles of ammonia at the beginning. So we can write that in as well. When equilibrium is reached, it's found that we have 25,5 grams of ammonia present. And then we're given the Kc value, it is 0,13. And what we have to find out is what is that X? What is the initial number of moles of nitrogen? So let's first strategize. What do we need to do to find that out? Well, if we could find out how much nitrogen reacted and how much nitrogen is at equilibrium, then we could solve how much initially there must have been. But how do we get that? We're given the number of grams of ammonia that we have at the end. If we convert that into moles, then we know how many moles of ammonia there were at equilibrium. We also then know how many moles of ammonia must have been produced in the process because we started with none. So if we then know how many moles of ammonia reacted, we can use that fact as well as the reacting ratio, 1:3:2, to tell us how many moles of hydrogen must have reacted to produce that amount of ammonia, and how many moles of nitrogen must have reacted to produce that number of moles of ammonia. So you see, then we're getting closer, because at least then we have one of these question marks that I wrote we need in order to find our X. So then how would we find this other question mark? How much nitrogen we have at equilibrium? How would we find that out? Well, once we know how many moles of hydrogen reacted, then we can use that to find out how many moles of hydrogen there are at equilibrium. We can then just work out the concentration, remembering that the volume is 5 decimeter cubed. Then we have the concentration of hydrogen at equilibrium and the concentration of ammonia at equilibrium. And then we can use Kc 0,13, as well as the concentrations, which by that time we would have known, of hydrogen and ammonia at equilibrium, and find the concentration of nitrogen at equilibrium. And once we have the concentration of nitrogen at equilibrium, as well as how many moles of nitrogen reacted, we can just work backwards to find what the number of moles of nitrogen must have been at the beginning. If that all made sense to you, then try now to work out for yourself what the answer is. If it didn't make sense yet, don't worry, let's go through it step by step. Okay, so the first thing is, we know that we've got 25,5 grams of ammonia at equilibrium. To make our table consistent so that we can make some progress, let's convert that to the equivalent number of moles of ammonia. So of course we need to know the molar mass of ammonia in order to do that. We look at the periodic table. The molar mass of H is 1 of N14. NH3 is therefore going to have a molar mass of 14 plus 3 grams per mole, which is 17 grams per mole. So make use of that information to find out how many moles of ammonia do we have if we have a mass of 25,5 grams. So we can simply substitute into the equation. N is equal to small m over capital M, 25,5 grams divided by 17 grams per mole. Or if you want to use the unit factor method, how many moles of ammonia do we have when we have a mass of 25,5 grams of ammonia? When we know that 1 mole of ammonia has a mass of 17 grams. Grams of ammonia cancel, we're left with mole ammonia, 25,5 over 17 mole of ammonia. We use our calculator. 25,5 divided by 17 equals 1,5 moles. So we know at equilibrium we have 1,5 moles of ammonia. How can that help us? Well, that means that 1,5 moles of ammonia must have reacted, must have been produced during the process, because we started with nothing. How does that help us further? We can then therefore find out how many moles of nitrogen and how many moles of hydrogen must have reacted in order to form 1,5 moles ammonia. How can we find that out? Well, we know the reaction ratio is always 1 mole is to 3 mole is to 2 mole. So we simply apply that reaction ratio to this particular situation where it's not 2 moles of ammonia that was produced, but rather 1,5 moles. So we have to deflate all of the values by that same factor. So how many moles of nitrogen and hydrogen must have reacted in order to produce 1,5 moles of ammonia? How many moles of nitrogen must have reacted in order to produce 1,5 moles of ammonia, when we know that the ratio in which these react is 1 mole of nitrogen for every 2 mole of ammonia produced. Notice, mole ammonia needs to be at the bottom to cancel away the given unit. Mole nitrogen needs to be at the top of our conversion factor to introduce the required unit. This ratio here comes from the balanced equation. 1 mole nitrogen for every 2 mole ammonia. 1,5 divided by 2, 0,75 moles of nitrogen must have reacted to produce these 1,5 moles of ammonia. What about hydrogen? How many moles of hydrogen must have reacted to form 1,5 moles of ammonia when the ratio in which they react is 3 moles of hydrogen needed for every 2 moles of ammonia produced. Moles of ammonia cancel. We introduce moles of hydrogen. Notice this reaction ratio comes from the balanced equation. 1,5 multiplied by 3 divided by 2 is equal to 2,25 moles of hydrogen. So we know that 0,75 moles of nitrogen reacted, reducing the amount of nitrogen from the initial amount, and 2,25 moles of hydrogen reacted, reducing the amount of hydrogen from the initial amount. And we already have the initial amount, and so we can therefore calculate what the equilibrium amount was for hydrogen. 8 minus 2,25 moles, 5,75 moles of hydrogen at equilibrium. So can you see we're getting closer to solving how many moles of hydrogen, because if we can just find out now how many moles of nitrogen at equilibrium, we can work backwards to how many moles therefore must have been present at the beginning. But how do we find that out? We're going to make use of Kc. We know Kc, it's 0,13. And we know that Kc means, in this case, the concentration of ammonia raised to its coefficient, in other words squared, divided by the concentration of nitrogen multiplied by the concentration of hydrogen raised to its coefficient 3. So we have the information needed to find out the concentration of ammonia. We don't have it yet, but we have the information needed. And we have the information needed to find out the concentration of hydrogen. So as long as we go and do that and just find their concentrations out, we can plug those numbers into this formula, and then the only unknown will be the concentration of nitrogen, which is something we're trying to find out. So let's then calculate what the concentration of hydrogen is and what the concentration of ammonia is at equilibrium, so that we can then use Kc to find the unknown, namely the concentration of nitrogen. So how do we find these concentrations? Remember, concentration is mole per decimeter cubed. In both cases, we already know the moles, and we also know the volume, the decimeters cubed. It's 5. So we simply need to divide these moles by 5 decimeter cubed, because concentration is number of moles divided by volume. We have the number of moles, and we know the volume is 5 decimeters cubed in each case. So we simply substitute the values into the concentrations. Here we're speaking about hydrogen, here we're speaking about ammonia. And we know that the number of moles of hydrogen that we have is 5,75 moles. We divide that by the volume of the sealed container 5,75 divided by 5, 1,15 mole per decimeter cubed. That's the concentration of hydrogen at equilibrium. What about ammonia? We know we have 1,5 moles of ammonia at equilibrium. We know that the volume of the container is 5 decimeter cubed. 1,5 divided by 5, 1,3 mole per decimeter cubed. So we have the concentrations of both the hydrogen and the ammonia at equilibrium. Now we need the concentration of nitrogen at equilibrium. We find that by substituting the values that we know into the Kc formula. So here I've done that. Concentration of ammonia is 0,3 at equilibrium. We raise it to the power 2. The concentration of hydrogen at equilibrium is 1,15 and we cube that. We don't know the concentration of nitrogen at equilibrium. That's the unknown. So we've got to solve for this unknown. To do that, we're going to have to rearrange this equation so that it's on its own. But how do we do that? All that, of course, is equal to Kc, and Kc's value is 0,13, we are told. Right, so how are we going to get the concentration of nitrogen on its own? Maybe the easiest way to do this is to realize that this is also a fraction, 0,13 over 1, and then to cross multiply. So that gives us on the right-hand side 1 multiplied by 0,3 squared, and it gives us on the left-hand side 0,13 multiplied by the concentration of nitrogen multiplied by 1,15 cubed. So that's what I have written here. So we still need nitrogen's concentration on its own. So how do we get it on its own? We must divide both sides by this other stuff. Remember, what you do to one side, you have to do to the other. So we're going to divide this side by 0,13 multiplied by 1,15 cubed, so that all of that cancels, leaving the concentration of nitrogen on its own. We have to do the same to the right-hand side, otherwise it's not legal. So we need to divide 0,3 squared by 0,13 multiplied by 1,15 cubed. So we put this into our calculator. 0,3 squared divided by, open brackets, 0,13 times 1,15 cubed, close bracket, equals 0,455. Notice, because nitrogen's concentration is not raised to any power, well, it's raised to the power 1, we don't also now still need to square or cube root the answer. The answer that we get here is the concentration, 0,455, and we're working out concentration, so the unit is molar, mole per decimeter cubed. So we now have the concentration of nitrogen at equilibrium, but we actually need the number of moles of nitrogen so that we can work backwards to find the initial number of moles of nitrogen. So we need to convert this concentration into its equivalent number of moles of nitrogen, remembering that the volume of the sealed container is 5 decimeter cubed. So we're asking ourselves, how many moles of nitrogen are present when the concentration is 0,455 mole per decimeter cubed? So we want to know small n, and we know the concentration, and we know the volume. So you work out, therefore, what's the number of moles? We simply substitute the values in the appropriate places. The concentration is 0,455, multiply that by the volume, and we find the answer 2,276 moles. So that's how many moles of nitrogen we had at equilibrium. Now we work backwards to find out how many moles of nitrogen did we have initially. If once we've used up 0,75 moles, we still have 2,276 moles left. So how much must have been present in the beginning? If you need an equation, here it is. X, which is what we started with, minus 0,75 has to equal 2,276. So what must x have been? Clearly it must have been 2,276 plus 0,75, which is 3,026. And there we found our answer, because the question was asking us calculate the initial number of moles of nitrogen.